At AWS, we believe that as a developer, there has never ever been a better time to build. Over the last couple of years, and especially recently, companies are going through large-scale digital transformations. With that has come an evolution of modern application design, utilizing APIs, microservices, and event-driven architectures. And of course, AWS to help build scalable, robust, and secure applications. The tools used to build these applications have also evolved, opening up new cloud operating models to help accelerate this change. My name is Arden Pikia. I'm an AWS Principal Solutions Architect working in the Developer Acceleration team here in Melbourne. And over the next 30 minutes, I'll be taking you through how to create flexible APIs to unlock organisational agility. First, we're going to explore the different types of cloud operating models that we observe in the field and the role that APIs can play in an organisation's digital transformation. We will then define the common API patterns that we see in modern architectures and take a look at some of the tools available to you at AWS to make those architectures a reality. Now, this is a little bit of a different talk. Instead of just diving into the technical details, I want to give you a sense of the impact that you as a developer and APIs can make when transforming your organizations. DevOps in cloud is not just a technology change. To get the biggest benefit and accelerate digital transformation, it requires a change in the process and culture of your organization. It requires a different way of thinking about this problem. Having been on this journey, I will give you some insight on how Amazon went through this same evolution and the impact you as a developer can have. So let's kick off with cloud operating models and APIs. Now, when moving to the cloud and adopting modern DevOps-based developer practices, we observe four main stages of adoption. The project stage is where most enterprises start, usually with a few projects or test environments to begin to understand how the cloud can meet a particular business need. Enterprises then progress through the foundation stage. It is here that they start to make some foundational investments, usually in the form of establishing cloud centers of excellence and building infrastructure like a landing zone, common tooling platforms, and establishing basic governance. As the enterprise builds a cloud foundation and gains experience with more projects, realizing its benefits, large-scale migrations are started. This often starts with an application discovery process and is usually followed by individual application migrations across a number of different migration strategies. Finally, at the reinvention stage, we observe enterprises having gone through this journey typically find themselves in a better position, having learnt along the way to better optimize both its IT footprint and business capabilities. Now, every organization's journey to cloud is different, but we often see enterprises stalling. We observe this happening most often around the time of the foundational stage of adoption. Now, there are lots of reasons why this happens. We see enterprises applying the same methods and processes that they used on premises to cloud. But digital transformation is not just where you take what you have in your data center and move it to the cloud. Developers need to be enabled on how to build modern cloud-native applications. They need to understand the new architectural patterns of building large-scale distributed systems. The three-tier monolithic architectures that we typically see on premises have evolved into microservices-based event-driven architectures, and with that, the organizational structures to support them have also evolved. Digital transformation requires change to technology and the organization. The three pillars of digital transformation and the developer experience are modern architecture and enablement, modern platform and tooling, and modern operating models together. Modern architecture enablement, where developers have access to actionable patterns and blueprints, and community-driven enablement within a sourcing. A modern self-service platform and tools with account and landing zone vending for on-demand environments and continuous detective and preventative-based controls. And perhaps most importantly, an operating model that support these new ways of working. The benefits to adopting these practices are huge. The DevOps Research and Assessment, or DORA paper, found that enterprises doing these things deploy code up to 208 times more frequently and had 7 times lower change failure rate. They were able to outmaneuver and out-innovate their competitors. Now, Amazon went through this same journey. Back in 2001, our architecture looked very similar to a lot of the three-tier monolithic architectures we see in on-premise environments today. We had a web tier executing traffic, a back-end application tier that processes requests, which was then stored in a large monolithic database. A lot of the integration was done at the database layer, with many stored procedures, and if you wanted to make a change, it would affect multiple teams. Now, there were many bottlenecks throughout this system. We needed not only a change in technology, but a change in the way we architected and organized ourselves. In 2002, a lot of this came to a head, and according to what is now an internet legend, a memo was issued by Amazon founder Jeff Bezos. Like all legends, a lot of this has been embellished and the details have changed over time, but this mandate would serve to form the backbone of Amazon in the modern web space. It came from the top, and adopting APIs was a catalyst for that change. We initiated a shift to microservices with the goal of decoupling. Each service was a small, independently deployable unit of code, decoupled based on scaling factors and functionality. APIs became the key contract between these services. No more integrating and communicating by the large database. Each service could potentially have its own state, so services had to be communicating via an API. This was strictly enforced. But a strange thing also happened. This led to changes in our organization. Now, many of you have probably heard of Conway's Law, which basically says organizations that design a system will produce designs which mimic the organization's communication structure. We found that small distributed teams will more likely produce modular service architecture than co-located teams. Decomposed microservices enable separate management and deployment. We were able to move faster respecting standard interfaces. The problem was our organizational architecture didn't fit with this. We aligned our organizational structure to our systems architecture. This led to small teams that would own these small services. We also invested heavily in automation. We were doing CI/CD before it was a thing. And by 2004 to 2006, the release process was completely automated. APIs was one component of this modernization. Organizational change was another. Now there's a great quote by Ruth Milan that is very apt here. If the architecture of the system and the architecture of your organization are at odds, it is the architecture of your organization that wins every time. The internet talks about the API legend memo, but it was only part of the story. We decentralized our organization to match the decentralization of software architecture. APIs was one component of this modernization. Organizational change was another. Now, this idea around organizing in a decentralized way isn't new. This is John Boyd. He isn't often talked about in IT, but his story is one of the stories we use to teach these ideas of decentralization and organizational transformation. Boyd was a fighter pilot flying F-86 Sabres. He was looking at what made these F-86s so successful, even though they were not the best planes in the sky at the time. Boyd, being what I would consider to be very Amazonian, looked at the data. It turned out there were two things that caused these F-86s to win consistently. One, it had a wider field of canopy, so it allowed a pilot to see more. Two, it had hydraulics on the controller. This allowed a pilot to scan the environment, make a change repeatedly. It allowed the pilot to out-iterate or out-maneuver the opposition. He came up with a theory called the OODA loop: observe, orient, decide, and act. He said the reason we are winning is because we can go through this loop faster than our enemy. We can outmaneuver them. Now this couldn't be truer today. It's not who has the biggest servers that wins, it is those who can outmaneuver. It's not the big eating the small, it's the fast eating the slow. Boyd looked at the way military was structured. They had big, centralized command and control that issued orders. Now by the time that order came down to the field, it was already out of date. So there was a lag between what you could observe and how you could decide and act. He said, we've got this backwards. We need to put authority as far down as possible. We need to put the authority where the data is. In our case, it's where the developers are. We need command and control, or the center, to give a mission. How you execute that mission is up to you. You have the authority because you have the data. So we see three mental models for cloud operating models: centralized, decentralized, and distributed operating models. We could say the military operated similarly to what we see in large enterprises today: big centralized IT teams with command and control type operating models. On the other end of the spectrum, we see a distributed operating model. We often see this in small startups where there is a lot of small teams working independently, but very little collaboration. We think there's a middle ground: decentralization, where there is some level of centralization, and these are usually things we don't want a developer to worry about. Things around security and governance and maybe some tooling. The rest is putting authority where the data is, empowering the developers. This is where the intersection of modern architecture, modern platforms, and modern operating models meet. Without APIs and self-service platforms, it is almost impossible to have efficient communication. APIs empower this model. Building your services with flexible APIs, we believe will also lead to organizational change. As developers, you are the agents of this change. So we've talked about the role of APIs in the context of organizations' transformation. APIs support an organizational transformation. We're now going to go through what makes a good API and then define some of the common patterns we see in modern architectures. An API allows two pieces of software to talk to each other. The protocols to do that are the languages and practice that allow this communication to happen. The protocols we most often see in modern web-based applications are REST, WebSocket, and the newer GraphQL type APIs. RESTful APIs use a request-response model that use HTTP to move application state. WebSocket APIs allow long-lived communication and open up a two-way channel between two pieces of software. I'll talk about GraphQL later and some of the problems it solves, but let's dive into REST first. The term REST was coined by Roy Fielding in his 2000 PhD dissertation, Architectural Styles and the Design of Network-Based Software Architecture. The dissertation presented an image of how a well-designed web application behaves. Fielding's dissertation was not a standard. We say an API is RESTful if it exhibits some of the behaviors in Fielding's paper. A resource in a RESTful API defines the things or objects against which we perform operations. They are usually the nouns in your application. For example, our API, we might have a note-taking application where we'll be working with notes, creating, reading, and deleting notes. The resource here will be represented by a URI, or Universal Resource Identifier. For example, the URI notetaker.io/notes would represent a collection of notes. The URI notetaker.io/notes/15 would represent a particular element or resource in that collection. We could then perform operations against the entire collection or an individual element in the collection. A method in a RESTful API defines the operations that will be performed on a resource. The operations represent a transfer of state against a resource, for example, a change in value. They are mapped to HTTP methods. For example, a post HTTP call would represent a create operation. So if you called a post on the collection resource, this should create another resource. In our example, a post against the notetaker.io/notes collection would create another note. If you called the delete against an element in a collection or resource, for example, the delete method against notetaker.io/notes/15, this would delete an individual note. Now, because REST is not a standard, the industry developed its own guidelines for what makes a good RESTful API. A model developed by Leonard Richardson, called the Richardson Maturity Model, breaks down the principal elements of REST into 4 levels or stages. Level 0 is what we see when URIs have actions in them. Things like amazon.com/add to cart or remove from cart. The problem with this approach, while simple, is that it makes it hard to discover the API. You have to know all the actions ahead of time. Do you use create or add or place to put something in the cart? Here, both the nouns and verbs are combined into the URI. Level 1 is when we see resources or the nouns in your application being used. Here, usually a single HTTP verb, like get, is used for all methods against this resource, with actions inside the body of the payload. Level 2 is what we often see as the minimum bar for a well-designed RESTful API. It maps typical CRUD, that is create, read, update, and delete operations, to HTTP verbs, post, get, put, and delete respectively. Level 3 REST APIs in the Richardson Maturity Model is HATIOS, or hypertext as an engine of application state. Specifies that a response should show how to progress to other states in the state machine. In other words, what actions are applicable from this response? Or what else can I do? The example on the right shows a response for a GET request on a particular film, but also contains links to get information on actors in the film. Now that we have some basic theory for REST APIs, let's take a look at some of the tools that we can use to implement them. Amazon API Gateway is a fully managed serverless service that makes it easier for developers to create, publish, maintain, monitor, and secure APIs at any scale. You can start small and then automatically scale. Being serverless, you can develop on a self-service platform that has granular costs, so you only pay for what you use, allowing you to experiment and try out ideas quickly and securely in your development phase. You don't have to manage servers and operating system patches, leaving you more time to concentrate on adding value to your application and business. Let's take a closer look at this fully managed API model. This diagram shows the API architecture of Amazon API Gateway. Now let's say you have a mobile, web, and other service accessing your REST API. The first thing that happens is that incoming requests arrive at one of our CloudFront POP locations. CloudFront is a content delivery network, or CDN, offered by AWS that allows you to distribute content with low latency and high data transfer rates by serving requests using a network of edge locations around the world. When the API Gateway receives the request, and if you've configured it to do so, its credentials can be authenticated with Amazon Cognito. API Gateway supports authentication and authorization mechanisms using Amazon Cognito or any standards compliant OpenID Connect or OAuth 2 tokens, without having to write custom code. It also supports Lambda custom authorizers to provide more control for fine-grained programmable access control. The gateway itself has strong observability, with logging and monitoring information in Amazon CloudWatch. The gateway can forward requests to a backend Lambda function, a web service running on Amazon EC2, or any other publicly accessible web service. You can even use the scalability of the cloud for your API and connect to on-premise backend services using endpoints in VPCs. Now, to build all of this requires the right tooling and security expertise. Your APIs are a customer-facing external resource, so it's important to maintain up-to-date web traffic protection. API Gateway leverages the AWS Edge Network services to secure your APIs. You can learn more about the AWS Edge Network at the following URLs. Now, RESTful protocols make up the majority of the APIs used today, but they are not without problems. Imagine you had a backend consisting of 3 separate microservices, each containing their own data store. You have both a mobile and a web client accessing these services. The first problem you have is the overfetching of information. Your mobile application might need a subset of the information that the APIs provide. So we've solved one of the problems of decoupling by moving to microservices using APIs and not having to integrate via the database, but we are now hindered by how the APIs are designed by the downstream microservice teams. The interfaces tend to grow over time as requests from different services come in to support new API responses and formats. Think about what this means from an organization perspective as well. We have to organize meetings with each of these teams to get support for an API call that our application wants to make. To get the data, you also have to make multiple calls across different endpoints and stitch together what you want in the client. And this is where GraphQL comes in. GraphQL is a query language for APIs. It allows the downstream service to define a service model for the APIs. The clients can then request only the data they need based on a schema that is published by the service. Now, you could run a GraphQL server, but then you have to manage another server and rely on scaling and securing that server. AWS AppSync is a serverless service that you can use to build scalable and robust applications over GraphQL with both real-time and offline capabilities. Best of all, no service to worry about. The protocol itself allows a microservice to describe the data and the operations on the data that is supported by the service. This means the API is discoverable and composable. You can then ask for what you want and only what you want. We effectively have a query language for APIs, so we don't have to compose these with multiple REST calls. There are 3 operations that are supported. A query, which you can think of as a traditional GET request in REST. A mutation, which changes data. Now this is usually a creation or modification request. And a subscription, which allows you to subscribe and get notified on events. This somewhat replaces what you used to need a dedicated WebSocket interface for. In this example, our schema defines a getPost query that gets a post with the ID of 1. Here, we are interested in the ID, title, author, and date fields. But we can ask for exactly what we need. In this case, we just want the ID and title field. No more composing multiple REST calls to get the data you need, reducing both overfetching and your response times in your application. We also have a create post mutation. In this case, you can think of this as a defined remote procedure call to create a new post. And finally, we have a subscription event that allows us to be notified on new post creation, returning ID, title, and author only. With GraphQL and AWS AppSync, you have a single request to a single endpoint to worry about. The complexity is solved in the back end, where the integration to services like DynamoDB, API Gateway, and AWS Lambda can be configured. You can now get the responses you need from multiple services without having to compose these yourself in the client. So we've talked about the impact moving to an API-first strategy can have on an organization. We also looked at some of the technologies used to implement those APIs. Let's take a look at some of the most common patterns implementing these in modern application design. Here we have the facade API gateway pattern. This is an external-facing API gateway that is responsible for routing incoming API requests to backend services. This solves a number of problems for clients. The backend services are hidden behind the facade of an API gateway. Clients don't need to make multiple calls to multiple backends. Now we can implement both a RESTful API or a GraphQL API gateway in this role. Using an API gateway facade has a number of benefits. It insulates the clients from how the application is partitioned into microservices. It also insulates the clients from the problem of determining the locations of service instances. We will look at both client-side and server-side discovery later. It also reduces the number of request round trips. Fewer requests also mean less overhead and improves the user experience. The API gateway often uses circuit breaker pattern, where if there is a downstream failure of a service, it can react in a controlled manner. A variation of the facade pattern is the backends for frontends pattern. Here, a specific API gateway is created for each client of the application. This way, you provide an optimal API for each client where translation can occur. Like with most things in computer science, both these patterns have some drawbacks. The API gateway is yet another moving part that must be developed, deployed, and managed. And this is where serverless solutions like Amazon API Gateway and AWS AppSync shine. GraphQL and AWS AppSync is a great fit for backends for frontends because each client can get exactly the data it needs, reducing the amount of data and response time in your applications. Backends for frontends is often combined with different microservice design patterns. Here we have a combination of BFF, backends for frontends, being used with event sourcing and CQRS. Now that's a lot of three-letter acronyms, so let's break that down. This diagram shows three parts. The backends for frontend part up the top, we've already talked about. In this case, the mobile application is making a hotel reservation request through the mobile API gateway. This brings us to the middle layer. It is here that we're utilizing CQRS, or Command Query Response Segregation. This layer contains two microservices, a reservation service, which takes commands, and a booking service, which we'll see later, which takes queries. All CQRS says is that you should separate your write model from your read model. Your write model is a data store that takes writes. In this case, it is contained within a microservice responsible for doing reservations. Once the reservation is taken, an event is generated. And this is where event sourcing comes in. Put simply, the event sourcing pattern is an append-only event log. It is a ledger of all the events in the system. You can think of it as a cross between an event bus and a data store that persists all these events. Events are stored sequentially in this append-only log. You don't store the final state, but rather the events that make up that state. So for example, here we are placing a hotel reserved event on the event store. We might store subsequent hotel cancellations or new hotel bookings as a stream of events, all with timestamps. Now this has some really cool properties. You have an inbuilt audit trail, which makes debugging easier. This is really important in a microservices environment because determining the overall state of an application is often spread across many microservices. The final state is calculated and stored in the query layer. In this layer, you play back the events to determine your final state. Just like a bank might store all the transactions in a journal, but only display your final balance in your app. In this layer, we could use a highly performant in-memory data store like Amazon Elasticache for Redis. Even if the state in this query layer is lost because of the use of an in-memory store, we can always recreate the state from the event store journal. In this way, we are utilizing a special query model and presenting it as a GraphQL schema, so the mobile API can get exactly what it needs. It is the best of both worlds in terms of performance and stability. This pattern is used heavily in very large-scale distributed event-driven microservices. If you can't go completely serverless for your environment and you are utilizing containers with clustering technologies like Kubernetes, this introduces a number of problems. These technologies are great for managing fleets of containers where the number of instances of a service and their locations changes dynamically. While this is great for decentralized teams, where each team can choose their technology stack for their microservice, this introduces another problem in the context of APIs. How does the client of a service, whether it's the API gateway or another service, discover the location of that service? We can solve this in two ways: client-side or server-side discovery. The first is using client-side discovery. In this case, the service instance first registers with the service registry. A service registry is like a phone book for all your microservices. It knows the locations of these services. HashiCorp Console and Netflix OSS Eureka are popular implementations of a service registry, which runs on AWS. The service client has a sidecar registry-aware client. This is a type of proxy that first checks the service registry for the location of the service, in this case, the flight info service. Once the registry-aware client knows the location of the service registry, it can route the request to the location of the service. This pattern solves the problem of service discovery with APIs, but introduces a few more. It couples the client to the service registry. While this might not be a problem internally in your organization, it means you are placing demands on something you may not control, i.e. an external client. Think about this in terms of decentralization of your teams and be aware of the coupling. Remember, architecture and organizational structure must be considered together. Server-side discovery can be used to get around this coupling by introducing another hop in the path. In this pattern, microservices still register with the service registry. But in this case, the client queries a router. The router then makes a query to the service registry. The router then forwards this request. Now, this can be accomplished with an AWS Elastic Load Balancer, for example. Container management solutions like Kubernetes run a proxy on each host that function as a server-side discovery router. Now, this comes with the cost of more network hops, but it is simpler on the API client as the implementation is abstracted away. So we've talked about the role of APIs in the context of an organization's transformation and look at some of the patterns used for APIs in a microservice environment. It is important to remember architecture and organizational structure need to be in harmony, so must be considered together when building systems. If we're going to adopt decentralized microservices, all with APIs, your organization structure should support this. But how do you do governance if every team has individual ownership of their microservices and APIs? This is where decentralized governance comes in. In a decentralized microservices-based organization, each service team operates independently from the other. Each team has members that are part of a community of practice, which helps set design tenets for software architecture, and in this case, APIs. Tenets are a set of guiding principles. Whilst each team is responsible for choosing the technology stack and implementation, they agreed to abide by these tenets. We want to make it as easy as possible through mechanisms to build APIs with blueprints and actionable templates. At AWS, we also have the concept of an API bar raiser. Bar raisers are a part of the Amazon culture, and it's our way of ensuring that whatever we build meets a specific bar in a decentralized organization. We use them in hiring, and we use them in software development. An API bar raiser is not a policeman. The service team ultimately has the final decision in the APIs. The bar raiser is there to make sure that they have considered the standards and have met the design tenets. How, i.e. the implementation, is still up to the service team. This is how API governance can be accomplished in a decentralized organization. So we've talked about cloud operating models and the role that APIs have in an organization's transformation. They can be an accelerator, but remember, if the structure of your organization and the structure of your software are at odds, it is the structure of your organization that will win. We talked about different API patterns and the technology used to implement them. The transition to DevOps, cloud, and modern architecture requires more than just tools, but as a developer, you're an agent of change in this transformation. If you want to learn more, we encourage you to get engaged with our training and certification content. There are a number of certifications and free digital courses that you can use to get started on your journey. With that, I want to thank you for your time. Now, we really value your feedback, so to help us improve our sessions, please share your rating out of 5. Happy building, and thanks for watching.